In this video, we're looking at some important ideas like SOH CAH TOA, the unit circle, and a method to calculate the sine and cosine of an angle. This is the first lesson of Unit 4, Trigonometry, as part of my Grade 11 Functions course. If you want me to teach you this entire course, visit my website, tutor.ca, and enroll in the second teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in Grade 11 Functions. I hope you enjoy the video. Hello everyone, I hope you're doing well. Welcome to Lesson 20 in the second teacher program's course on Grade 11 Functions. Here we're taking a look at similar content in section 4.1 from our textbook, which is special angles. And this introduces, the first chapter in our trigonometry 2 units. We have a double, 2 units. The two following units are going to be about trigonometry. This one is just called trigonometry, and the next one is called trigonometric functions. So we look at them more as, we look more at the graphs of the functions and kind of like the last unit, which was exponential functions. We focused on that specific kind of function. In the following unit, we're going to focus on the specific kind of function, which is the trigonometric functions. But first, before we do that, we have to get a lot more comfortable with them. How do we calculate all these kind of angles? We have to do a lot more work on trigonometry. So this next chapter, even though we're going to use a lot of functions, we're not really going to think it's going to be a little bit different than the rest of the course. We're really just focusing on developing our trigonometry skills. This is going to be kind of like those side units where we do like what's a radical, or working with fractions, or what we did in the last unit, which was like rational exponents. Those little side sections that are just to develop a skill. This whole unit is to develop a skill, and the skill is trigonometry, okay? So we begin with this section right here. We begin with special angles, and I just want to quickly go through maybe a little outline of what to expect in this unit, okay? Because I think it's good to have just like your sights set, if that's the correct saying, for where you're going. So I'll just actually take a screenshot quickly of the textbook sections here. So oops. So chapter 4, trigonometry, I made that a little too big, is we start out with special angles, okay? And so these first two chapters are essentially just developing our skills in identifying the names of things in trigonometry, and also how we calculate angles. And by angles, I mean how we calculate the sine and cosine and tangent of angles without using a calculator, essentially, right? Because for a lot of trigonometry, you could just plug it into a calculator, but this chapter is trying to define, like, how does the calculator figure out all that stuff? What is the math behind the calculator? That's what this chapter is about. So then we talk here about reciprocal trigonometric ratios, right? It's another set of trig functions, which are very related to the original ones. They have funny graphs, and you'll see what that is. And then we have problems in 2 dimensions, problems in 3 dimensions. This is just a bunch of word problems and real life physics problems, essentially, right? In 2 dimensions, and then we do talk about 3-dimensional stuff. And this is probably the first time we've ever talked about 3-dimensional stuff. I can't think of anywhere else where you would have that. So anyways, just a bunch of word problems to use this stuff, to use everything we just learned, and a lot of triangles, right? And then trigonometric identities. Well, this is actually a really interesting chapter. This was one of the hardest for me when I took this course originally in grade 11. And I find it very interesting, and I love teaching it, because it's sort of your first introduction to like proofs. In the last unit, we talked about proofs. We talked about one proof of the rational exponents, right? We showed that, well, 1/1/2 means the square root. An exponent of a half means the square root. So we proved that. And so trigonometric identities is all about proving equations, okay? So we have some sort of equation that's true that involves trig functions, okay? And all that stuff you're going to learn about in this section. But we're proving that it's true using what we know, and it's a very interesting one. Takes a little bit of practice. It takes a lot of practice, I'm gonna be honest, but very satisfying, very interesting. I think it's very fun to prove things even at this level. Okay, so there's our general introduction to chapter 4. I'm gonna be making reference to my notes a lot in this lesson because I have a very, very detailed set of notes for this lesson, just so that I cover everything and get all the important details in. So yeah, as I said, next 2 units are trigonometry. This one is working on our skills. Next unit is actually trig functions. And then just want to mention, we build up from what you know in grade 10. So I'm going to do a little review of basic trig. That's the first section of this. It's just, well, not just a little review, a review of basic trig. And then from there, I will go on to developing what we want for this section. Okay, so let's begin. I'm going to start our review. So this is going to be the beginning of our review of, uh, of, uh, I'll call it basic trig, right? Because we're going to go into more advanced trig today. So I'm going to call it basic trig just because it's the old stuff, right? So review of this, well, okay, so let's begin by drawing out a triangle that I have here. Okay, so the side length, the first side length is going to be 3. Okay, the next side length is going to be 4. Like that, and then I'm going to connect the two sides like that with a line. Okay, so let me label all the stuff here. So that's a right angle. That length is 4. That length is 3. And I'll just tell you that that length is 5. In fact, we can calculate what that length is. So we can do that by the Pythagorean Theorem, which is a squared plus b squared equals c squared, right? These two are the two shorter lengths. Those squares add up to the longer length. This is the longer, right? Which the longer one is also called the hypotenuse, right? Maybe you remember that. So I can plug. I'm looking for the longer length, right? So then I'm trying to identify. Okay, well, 4 squared plus 3 squared equals c squared. 4 squared is 16. 3 squared is 9 equals c squared. Okay, 25 equals c squared. Okay, and now so 25 is c squared, but I want c. I don't want c squared, right? So I'm going to take the square root of both sides. So the square root of 25 equals c. Right? We only take the positive square root because it doesn't make sense for a length to be negative. A length cannot be negative, so we only take the positive. So 5 equals c. And so we get that that length right here is 5. That's one way to make a triangle that exists. You know, I could put any number I want here, right? I could say, oh, that's 6, right? But this is not a triangle that exists. One side 4, one side 3, and one side 6 with a right angle in there, right? The only one that exists is the one with a 5 there, right? With the rest of these numbers in place, right? But I'll talk more about that a little bit later. So what if I have this triangle like this, right? And then I have another triangle, a very, very similar triangle, okay? But it's going to be exactly, now let me try to draw it here, right? It's going to be exactly twice as big. Let's see if I can do it. The bottom length was 4, so now I want it to be 8. So that's 8, right? Yes, and the top length is 1, 2, 3, 4, 5, 6. There, that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. Good. Okay. So essentially all I did was I doubled the size. So all the lengths will be double. It's going to be 8 here, 8 here. It's going to be a 6 here. It's going to be a 10 here. Right? I just doubled all the lengths. So the same triangle, really. Oops. Same triangle, but I've just made it twice as big. Right? So we're going to focus in on these two triangles here quickly, right? All I've done is I've scaled one up compared to the other, right? By a factor of 2, right? By a factor of 2. And that just means multiplied everything by 2 in there, right? So now what I have to ask is, are the angles the same? That's the first question. This angle here, is that the same as this angle here? And this angle here, is that the same as this angle here? Well, the answer is going to be yes, because the distance between the legs of the triangle, the sides of the triangle, has not changed, right? The lengths of the sides has changed, right? But the angles themselves stay exactly the same, right? Because I'm not warping the triangle, I'm just stretching it, and I'm stretching everything equally. So usually we like to, I did it with colors here, but usually we like to give symbols to the angle. So the very, very common symbol that we give to angles, there's two very, very common symbols, and one is more common than the other. In fact, one is used entirely. One's called theta. Now, I'm sure you've seen this before, but one's called theta, and I draw it like that, okay, when I'm writing. But maybe I'll show you quickly what it looks like. Maybe I'll show it in LaTeX here. I'll show you what the actual symbol looks like. Let me just do that. So, it's like an O, sideways O with a line through it, right? There's a whole bunch of ways to draw it. In fact, I can just Google theta symbol, right? And you'll be able to see that there's actually a whole bunch of ways to draw this theta. So that's the most common one, really. That's pretty much the most common one. Just a circle with a line through it. So you pronounce that theta, like I have here, right? But I draw it like this, again, so it's a little O with a little curve through it, okay? So whenever I draw this symbol, that's theta, it represents an angle, And then the other most popular one is called phi. Okay, these are all Greek letters, right? In math, we use Greek letters to be fancy, really. I mean, we could use any symbol, but just because they're already recognizable, they already have names, they already have they have like a form, like have a standard way of drawing them, right? Then we chose to use, not like I chose it, but like mathematicians just chose to use Greek letters for all this stuff. Phi is another one. Phi is a little bit simpler. It's an O again, but with a line like that. Okay, well at least that's how I draw it, right? So it's a little O, a line vertically through it. Okay, so that's theta, that's phi. Okay, both of these are just symbols. Doesn't matter. They're just variable names. I could call them x and y. Doesn't really matter. But the standard is to call it theta and phi. And you can call it whatever, absolutely whatever you want. But I will be calling the two angles theta and phi inside of a triangle, right? So theta is the main one, phi is the other angle, right? I mean, yeah. So there we go. That's just so there's no confusion about what I'm saying when I say theta and phi, right? They're just symbols. That is how I draw them. I'll show you how to draw phi. We're interested in phi symbol. It looks like that. So that's really how I draw it. It's like an O with a thing like that. But sometimes it's drawn like that. Sometimes it's drawn like that with a little serif on it. But yeah, that's the idea. Okay. Again, just to avoid any confusion. There we go. So I will call the red angle theta. Okay, and I'll call the green angle phi. So to do that, I'm just going to go in here and I'm just going to label it theta. Right, little tiny theta. And I'm going to label this one phi. So I'll label this one phi. And this one theta. Okay, so now we have theta and phi here in our triangle. And I want to just note here that those angles are the same. Of course, I labeled them the same in both triangles, so they must be the same, right? And the 90-degree angle is the 90-degree angle, right? That doesn't change. Okay, interesting, right? So it doesn't matter that if I scaled up a triangle, I made a change to it, but something stayed the same. The angle stayed the same. In math, we really like that. Whenever there's something that we make a change, but something stays the same, it's called an invariant. And you can use that to your advantage in a lot of problem-solving situations. Okay, so let's take a look at just something you might want to calculate when you're doing working with triangles here, right? You might just happen to say, well, what's the ratio of the sides, right? If I take one side and divide it by the other, what happens when I scale it up, right? So let's, for example, take I'll say this is our focus angle, right? Theta is usually, I'll call it our focus. Right? Focus angle is theta. And so I'll label all the sides according. Well, this number 3 is opposite to it, right? This number 4 is adjacent to it, right? And then the 5 is, well, that's the hypotenuse, right? So I just gave them all names. So what if I wanted to calculate the opposite side over the hypotenuse, right? Hypotenuse, oops. The ratio of these two things, right? Well, the opposite side is 3 and the hypotenuse is 5, right? Then let's take a look here. What about in this triangle, right? Again, that's our focus. So this is our adjacent side, this is our opposite side, this is our hypotenuse, right? And again, what if I wanted to calculate the same thing, right? Well, I would get 6 over 10, right? Opposite over hypotenuse, 6 over 10. But that simplifies to 3 over 5. So, interesting. After scaling, right, the triangle, in fact, I'll write that down here. After scaling the triangle, the ratio of the side lengths did not change. It was 3 over 5 there, and it was 3 over 5 there. Again, whenever there's something that doesn't change, you can use that in math, right? You can use that. There's something you can use there to solve problems with. So that's interesting, right? So it looks like the ratio of the sides does not depend on the length of the sides, right? The length of the sides does not change what the ratio is, right? Because the sides were 5 and 3 on this triangle and 6 and 10 on that triangle, but the ratio didn't change, right? So the ratio does not depend on the length of the sides. Okay, so what does it depend on? That's what we're trying to figure out. What does it depend on? And so it actually depends on something entirely different, right? So you could do this for you can do this for any combination of opposite, hypotenuse, and adjacent. Make any fraction you want, and there is a the ratio doesn't change, right? So, but the three main ones, the ones we usually care the most about, is opposite over hypotenuse, right? Adjacent over hypotenuse, okay, adjacent over hypotenuse, and then opposite over adjacent. And yeah, you can make other combinations. I'm not saying these are all the combinations, but these are called the three primary ones. Okay, these are the primary ones. So let's just do it quickly. Adjacent over hypotenuse, 4 over 5. Okay, and then over here, so if I just like say, okay, well, I'm doing that for this triangle as well, right? Adjacent over hypotenuse is going to be 8 over 10, but 8 over 10 simplifies to 4 over 5, right? So it didn't change. The ratio didn't change. And then finally, opposite over adjacent, that's going to be 3 over 4. And then, as you might expect, in our next one here, right, opposite over adjacent is 6 over 8, which simplifies to 3 over 4. So you see that also didn't change. So what does it depend on, right? What does the ratio depend on? It doesn't depend on the side lengths, because if I change the side lengths, right, or yeah, if I multiply the side lengths by something, it doesn't change the ratio, right? Of course, if I just like add 2 to 3 and it's like 5, 4, 5 triangle, that triangle just doesn't exist with these same angles, right? You're just completely changing the triangle, and at that point you have nothing that is invariant, right? You have nothing that's staying the same. So you don't want to do that. You just want to be able to scale up triangles, right? You don't want to just add to the lengths. So well, so it looks like it doesn't depend on the length of the side lengths. We call these things, right? You probably remember SOH CAH TOA from grade 10, and we're going to go into why we give these things names, right? And so essentially the idea is that if I take this triangle here, right? Okay, so I have the triangle here set up. I decided to do it in a little program like this, right? And so we already saw, let me just note what we have here, right? We have our 90-degree angle here, side length 3, 4, 5, right? We have our, it doesn't really matter the exact value of the angles here, right? But it's 53 and 37 approximately, right? So let's take a look here. Now we know already, if we focus on one of these ratios here, right? So for example, this length here is 3 and this length here is 5. So if we look at the ratio opposite over adjacent, right? Opposite over hypotenuse, right? Which was one of them that I mentioned here, opposite over hypotenuse, right? We have 3 over 5 here for this triangle. And we know if we scale it up, we still have 3 over 5. But what I want to show is that if I change the angles inside of the triangle, that ratio changes, right? Because we're really changing the triangle at that point if we change the angles inside. So you see here, let's take a look. So if I have, if I take that angle here, so let me rewind to what we were before, right? So focus on this angle down here, right? That angle right where I'm circling there. That is our focus angle, 36.9. And if I just move one of the points, for example, move this up here, I'm changing almost all the angles inside the triangle. Now, notably, this angle is still 90, right? I'm going to leave that angle as 90 because we're only working with right angle triangles right now. But I've changed the angles inside, and now look at the ratio. The opposite over hypotenuse is 4.6 over 6.1. Well, that's definitely not, if I look at 4.6 over 6.1, that definitely is not the same thing as 3 over 5, right? It's definitely not the same thing. Yeah, so if I put this into a calculator, I get about 75%, right? That's about 75%. And 3 over 5, right? 3 over 5 is about 60%. So it's pretty close, but it's not exactly, right? The ratios are not the same. Because we change the angles, right? So the ratios are going to change themselves. And so you see what we just discovered there essentially is that the ratio of the sides of the triangle or of a right angle triangle is dependent on the angle or the angles inside the triangle, right? Specifically, we look at theta, okay? That's the one that we really want to look at, the focus angle. You could choose this angle to be your focus angle, but then you're really just kind of turning the triangle to the other side, right? So you always kind of choose a focus angle, and we say, well, based on that theta, based on that angle theta, what should opposite over hypotenuse be, right? So we're essentially saying for the angle theta, what is what is opposite over hypotenuse, right? Hypotenuse. And then we ask the rest of the questions just the same. For the angle theta, what is the opposite of hypotenuse? Then we go on to adjacent over hypotenuse. Adjacent over hypotenuse, okay? And then we also say, well, you can do any combination, right? But these are the primary ones. Opposite over adjacent. Right? And so instead of, writing, so this will give us one answer. I should just note here. This will all give us one answer. Give us one answer each, right? One answer each. So since we get one answer each, it's kind of like a function, right? You take in an angle theta, and then you get what the ratio is out. You take in the angle theta, you get what this ratio is out. You take in the angle theta, you get what this ratio is out. So we give all these functions special names, okay? And so we give this one the name sine, okay? We give this one the name cosine, and we give this one the name tangent. Okay, so let me just give the full names, I guess. So this is sinus, cosinus, and this is tangent. But of course, you don't really say that. That's the big word. So you just say sine, cos, and tan, right? But these are functions, so they take in an angle theta. They take in an angle theta, and so this is not multiplied, but this is not cos times theta. This is cos of theta, just like I did f of x, right? Essentially, I've just labeled my f. The name of my f is just like I've named it 3 letters: cos, tan, and sine, right? And so these are all functions that when you put in some angle theta, it gives you what that ratio should be. Okay, so if I say like sine of 25, what this is saying is it's saying, oops, didn't mean to put a line. Oops. What this is saying is that in a right angled triangle with one angle being 25 degrees, okay, what is the ratio of the sine was the opposite over the hypotenuse. What is the ratio of the opposite over or opposite side length over the hypotenuse, right? And you see that this, the interesting thing is that this gives one number, right? There is only one number that is sine 25, right? It's the ratio of the two sides in a triangle with an angle of 25 degrees. Notice we don't have that much information about the triangle here. We only know one angle inside of it, and we know it's a right angle triangle, so I guess we know 2 angles, right? But what we know is that there's only one answer, because you see, the ratio of the sides does not depend on which triangle we choose, the bigger one, the smaller one, if I stretch it out to anything in between or anything like that. It doesn't depend on which one. It just depends on the angle. The angles inside. That is what determines the opposite over the adjacent over the hypotenuse, the opposite over the adjacent, all of that. I think I said opposite over adjacent twice. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Okay, and so that's why we give all these special names to these particular ratios. Right? So they are functions. Very notably, they are functions. Okay, so they take in a number and they put out one number. Right? You can graph them. We're going to talk about the graphs of these functions in the next unit. Right? You can graph them, but we're going to leave that for now. For now, just think of them as just functions. Right? And so let's take a look. Let me just look at my notes here quickly. We give them names. It takes an angle and outputs a number. So it takes in an angle, notably, right? So it's but an angle can be really any number. An angle can also be negative, right? Stretching the triangles doesn't change the ratios. And so one way to remember this, right? One way to remember this, that essentially that, well, so let me actually write the formal I haven't written the actual definitions here. So these are called the primary trig ratios. Okay, these are called the primary trig ratios. Okay, and so sine of theta is equal to opposite over hypotenuse. Okay, cosine of theta is equal to adjacent over hypotenuse. And again, these are just names. I didn't decide, but some mathematician decided that cosine would be that ratio and sine would be that ratio, right? not really arbitrarily, not like just for a random choice, right? But the names are kind of random, right? The name sine is actually a mistranslation of some Latin text. I don't know the full story about that, so I can't get into it. But I know it's a mistranslation, and then cosine is essentially just sine with the word co in front of it, and tangent means a whole other set of things. But yeah, so the names are just names. What's important is what ratio they represent. So tangent is opposite over adjacent, right? So now sine theta, right, is opposite over hypotenuse, right? Well, so we can remember all this, these three primary trig ratios, right? Sorry, I think I'm blocking the camera a little bit. There you go. By the mnemonic SOH CAH TOA. And in fact, I still repeat that in my head to this day to remember the ratios, right? So SOH CAH TOA is what we essentially have. Now, that doesn't mean anything, but it's just sort of like something you can remember, right? A lot of people can have easier time remembering SOH CAH TOA. And so this represents that sine is opposite over hypotenuse, right? Cosine is adjacent over hypotenuse. Tan is opposite over adjacent, right? And so that helps you out. Okay, so let's begin with a little example here that's going to help us out, just to refresh ourselves on using SOH CAH TOA. So if I just draw a triangle like this, right? It's a right angle triangle. Now ignore that little extra bit. I'll just erase it. Oh boy, this is going to be hard. Oh boy. Okay, I'm just gonna go. just ignore that little bit at the end. So if we have, for example, some triangle like this, it's a right angle triangle. In here, I'm gonna say there's a 60-degree angle, right? And I'm gonna tell you maybe this length right here is, I don't know, 25, whatever, 25 units. Doesn't matter really the unit. And I say, well, maybe I want to find the opposite side here, right? Opposite side. Okay. So how we do this, in fact, let's just say we want to find all the sides now, right? The opposite side and the hypotenuse, right? Now you couldn't do this with anything else. You need SOH CAH TOA to be able to solve this, right? And we're going to use our primary trig ratios, so sine, cosine, and tangent to solve this, right? So our goals are to know what the hypotenuse and the opposite side are, knowing an angle and a side, right? We know an angle and a side. Now think about this for a second. Do you have enough information to solve this problem? If I gave you, right, a stick that's like 25 centimeters long and an angle, would you be able to complete the triangle from that point? And I really want you to take a second and think about this. Maybe even get a stick and imagine it, right? I don't really have anything here, right? I like this, right? If I give you a stick and I give you some angle that the arm has to go at, you don't know how long that arm is, right? But you do know that there's a right angle here. So it's going to meet up like that. So you see that, yeah, in fact, you do actually have enough information to build a triangle, right? And if you can build the triangle, then you do have enough information to solve the problem, right? Because then you could just go there with a ruler and solve it. But we want to try to do it without having to build it. But just thinking about if you can build it is a really good way to think about how do we know when the problem has just one solution, right? So this just has one solution. So to find the opposite and hypotenuse, we're going to need to use the primary trig ratios that have opposite and hypotenuse, right? But also have to include the adjacent, right? So the opposite sine here will not be helpful because we don't know what the opposite or the hypotenuse is, right? But cosine, right, would be helpful to find the hypotenuse, right? And tan would be helpful to find the opposite. So let's start with tan here, right? I'm going to take that down. I'm going to rewrite that here. So tan of the angle theta is equal to opposite. Now, opposite was what we're solving for, right? Opposite over adjacent. Okay. And so now we have tan theta equals opposite over adjacent. Now we're looking for we're looking for opposite. So if I just substitute in what I know theta. So this is tan of 60 degrees equals opposite over adjacent is 25. Right? Then I can pretty much just solve for the opposite side. Right? I can just solve for it. The opposite side is going to be, well, multiply both sides by 25 here. Right? Multiply both sides by 25. We have 25 tan of 60. Oops, 60 degrees. Right? And that is our opposite length. And the thing is that our calculator already knows what tan 60 is. Right? In fact, that's something we're going to do in this section. I know we're probably already way into the lesson now, so it's going to be a long lesson. But tan 60 is going to be something that your calculator already knows. And so we're going to see in this lesson, how do we find tan 60? Okay. that's that. We can plug this into a calculator. 25 times tan 60. Now make sure your calculator is in degree mode. There's another way to measure measure angles called radians, and you don't want that. So you know your calculator is in degree mode if you see a little D on the top of the calculator on the screen. So anyways, I plug this into my calculator. I get 43.30127. So now a lot of these, whenever you plug in a trig function into the calculator, the decimal will go forever. Like it's not, you have to round eventually. A lot of the time, not all the time, but a lot of the time. Okay, so 43.3, let's just say, is our opposite side, 43.3. And now our hypotenuse, well, we can do it in two different ways, but let's do it with cosine now, right? Or yeah, let's do it with cosine. So remember that cosine theta is adjacent over hypotenuse. And now hypotenuse is the thing that we're solving for, right? Hypotenuse is the thing we're solving for. What do I know? I know theta is 60. I know adjacent is 25, right? So this is actually cosine 60 equals 25 over the hypotenuse, right? And so now what I can do, I'm going to solve for hypotenuse now, right? So how I'm going to do that is I'm going to multiply both sides by hypotenuse. Right? Kind of like solving for x, exactly like solving for x in the denominator there. You need to multiply both sides by hypotenuse. It cancels there. And then you just have, well, let me use the red again. Then you just have hypotenuse times cosine 60 equals 25. And now what you want to do is you want to divide both sides by cosine 60. Now notice, I didn't divide both sides by cosine. I didn't divide both sides by 60. Neither of those things are exactly here. There's no 60 and there's no cosine. There's cosine 60. That's one thing. Cosine 60 is one thing, right? You can't separate the cosine from the 60. Just like you cannot separate, f of 2. That's not f and 2. That's f of 2. That is one object there, one symbol, right? So cosine 60, just the same. We do that so that the cosines cancel here. And now we see that our hypotenuse, the thing we're solving for, is 25 divided by cosine 60, right? And so we just plug that in. 25 divided by cosine 60 is 50. So that was helpful. So the hypotenuse has a length of 50. So you see how that one was not an infinite decimal. It actually was just exactly 50. So this is 50. And that's a triangle that exists, right? If I gave you a stick that's 25 meters long, 25 centimeters long, whatever, and an angle of 60, right? Then that hypotenuse would be 50 centimeters long, and the opposite side would be 43.3, right? And that just happens to be what it's going to end up being, and we've solved that using these ratios. Okay, so I'm going to move on. We got a lot to go through in this lesson still. I got 2.5 more pages of notes. So we will definitely make some progress now. But that's pretty much everything for the review of trig, right? Now let's move on to what we're going to talk about in this lesson. And essentially, what we're trying to answer is, how does the calculator know the trig ratios, right? How does the calculator know the trig ratios? Right? That's our question, right? If I type in sine 60 into my calculator, how does my calculator know what sine 60 is, right? So we're going to particularly be looking at the angles 30, 60, 90, 45, and then multiples of those angles, right? So we got a little way to go. And we're going to be using a bunch of tools that we have to develop this kind of stuff. And yeah, we're going to start that, right? How does the calculator know? Now, of course, if you type in sine 60 and you get a number out of it, right, that'll totally work, right? It doesn't matter if you know where that number came from or not. But to develop our understanding of math, right, to help you along solving problems in the future, right, knowing where these things come from is definitely important to progress in math, right, to get to another level. Okay, let's get started. Oh yeah, before I move on, there's actually one last thing I need to mention, and that's the identity here, that when I'm trying to find all these ratios, if I'm trying to find sine theta, cos theta, and tan theta for some particular angle theta, right? If I'm trying to find that, I actually only need to find sine and cos, okay? And the reason is that there's an equation, in fact, an identity, which is something I mentioned at the beginning of this video. There's an identity that relates sine and cos to tan. So the fact is that, look, if you remember, sine theta equals opposite over hypotenuse, right? So I'm going to use just O and H here for opposite and hypotenuse, right? And cos theta equals adjacent over hypotenuse. Okay, so if these are equal and these are equal, what if I divided them, right? If I did sine over cos and opposite over hypotenuse over adjacent over hypotenuse, that would still be equal, right? So let me write this a little nicer, right? This is sine theta over cos theta equals opposite over hypotenuse over adjacent over hypotenuse. Okay. So that's still equal, right? Why would we want to do that? I don't know, right? We're not there yet. Okay, but now that we see that sine theta over cos theta is opposite over hypotenuse over adjacent over hypotenuse, let's divide these fractions here. So remember, the fraction over a fraction is you just multiply by the reciprocal, right? So sine theta over cosine theta is equal to opposite over hypotenuse times hypotenuse over adjacent. The hypotenuses cancel here, right? And what we're left with is sine theta over cosine theta equals opposite over adjacent. But what's opposite over adjacent? Try to remember from SOH CAH TOA. That's just tan theta. So we see that sine over cos is tan. So if you ever figure out what sine of an angle is and cosine of an angle is, just divide the two and you're going to get what tan of that angle is. Okay? And so that's just a property. This is, you know, our first trig identity, really, is what we should call it, right? It's an identity. This is true for every value of theta that you put in, right? That sine over cos, sine theta divided by cos theta is equal to tan theta. Now that we know that, whenever I say, you know, let's solve for, you know, the primary trig ratios of, you know, an angle 60, you know, we only have to find sine and cos. If we know sine and cos, we can find tan. Okay, so there we go. We have that done. So let's take a look now at the beginning, right? So our goal is to find a method to calculate sine and cos of an angle. Goal is to find a method to calculate sine and cos of an angle. Okay, now that we have that goal in mind, right? What we know right now is the primary trig ratios. Right? That's this stuff. That's exactly this right here. So I'm going to erase that. But these are the primary trig ratios. Okay, so we know this much. Okay. I'll just copy and paste that back down here, right? So we know this. Okay, so the first thing that we use to go through this stuff, to be able to get an angle like this, in fact, let me just help you out here a little bit, just to mention, I have a bunch of pictures in my notes, so I'm going to just use those pictures, right? So that this is probably a nicer diagram, right? So the first tool that we use is called the unit circle. Okay, so the unit circle looks like this. Okay, it's essentially a circle. Now the reason it's called the unit circle is because it's a circle. Unit circle means it's 1 unit. The radius is 1 unit. So you see from the center to the edge is 1, 1, 1. So that's why it's called the unit circle. Okay, so we have that here, right? And so not too difficult to draw, right? This is just a little additional tool that we're going to be using to help calculate our ratios. Again, we're trying to figure out how do you find the sine and cos of an angle, right? Without knowing the exact, well, you'll have to know something about the triangle, but you know, assuming you just have it in a calculator, right? If you type in sine 30, how does the calculator figure out sine 30? Or how did we figure that out originally? So the next thing that you want to do, okay, is draw an angle, right? Start at the origin, right? And draw essentially an arrow coming out to touch the circle from anywhere. I mean, from the circle, from the center, but to anywhere on the circle, right? Technically, this is called a vector, but since this is the only vector we see in this course, I'm just going to call it an arrow. But for future reference, it's a vector. You'll hear about vectors in grade 12. So this arrow right here, the fancy name for this arrow in the way we're using is called the terminal arm. Okay, so it's called the terminal arm, and you'll see there are other arms in this whole setup, right? The whole goal of this is to find theta, find cosine theta, sine theta, and tan theta for some angle theta. So that terminal arm, doesn't matter where you draw it. You could draw it over here too, but for now I'm going to stick in that first quadrant, right? So quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? That angle makes that arm makes an angle theta with the x-axis, right? The positive x-axis. And we call that positive x-axis the initial arm. Initial arm, okay? It makes some angle. Doesn't matter where I draw it, it makes some angle there, right? So we're going to try to find the sine and cosine of that angle using the circle around us. Okay? We're very interested in that angle. Now, let me open another picture just because I want to keep this as clean as possible, because this definitely gets confusing, right? So there is another image here to help you out, right? There's maybe a cleaner one. Right? So we just have the arm coming out. And then we're very interested as well in the point where the arm, the terminal arm, right, and the circle intersect. That point right there. Let's call that point XY, because it's an XY point, right? So that's kind of like there. I have it highlighted there, XY. Okay. So we're going to show how theta, the goal is we're going to show how sine and cosine relate to x and y, right? I should say sine of theta and cosine of theta relate to x and y, not t. Right? So to do that, we're going to draw a line. We're essentially going to make a triangle here, right? So we're going to draw a line going straight down and a line straight across here. We're going to make a right angle triangle like that. So let's take a look at a nicer diagram of this. Essentially, well, actually, before I do that, I just want to note some things here, right? So we're going to draw a triangle down, right? A length down from that point, and then a triangle. Remember, that ray, terminal arm, is making an angle theta with the initial arm, or with the x-axis, the positive x-axis, right? Not the negative x-axis, the positive x-axis. Okay, so we have here this triangle. Let's just quickly note, what do we know about this triangle? Well, first of all, I know that's an angle theta. I know that's an angle 90. I know this length, actually, the hypotenuse. I actually know that length. Because look, it's the radius of the circle. And by definition, it's a unit circle. The radius is 1. Right? So that length is 1. And then I know this side length. Well, I don't know the number, but I know I'm going to call it opposite, right? I'll just leave it O for opposite, and adjacent for the adjacent one. So a little bit in a more clean way, here's that diagram. Now, sorry, the quality is so weird because I'm taking a screenshot of a thing, and hopefully the video quality is okay. But essentially just says unit circle. Let me just draw things in better. So theta, 90 degrees, h equals 1, and this is an opposite and an adjacent, right? That's all it is, right? So now that we have this, now that we know like the shape we got here, right? Let's actually have the original screenshots. That might be better. You know what? I'm not going to go through it this second. Open the folder quickly, see if I can find it. But if not, just leave it. Yeah, no, look, sadly. Okay. So we have here. This is the situation we have now, and so I'm going to try to show you how does x and y, the point xy, relate to theta. Okay, xy relate to theta, and specifically the sine and cosine. Well, you'll see it's going to end up being the sine and cosine of theta. First thing I want you to notice now, okay, let me just make sure I'm going through my notes properly here, right? So draw a straight line down, adjacent, right angle triangle, hypotenuse is 1. Okay, so first thing to note is that this point xy here, right? X is the distance from the y-axis, or how far along the x-axis you go, right? And the y value is how far up you go, right? Well, that number is exactly the x distance is how far along the x-axis you go. Well, that's just adjacent. That's just a, right? The length a is how far you go along the x-axis. And similarly, the length O is how far up you go from the x-axis. So what we kind of just determined here is that the x value is equal to the adjacent side, and the y value is equal to the opposite side. Right? So just make sure that makes sense to you before we move on, right? The x value is equal to the adjacent length. The y value is equal to the opposite length of that point right there, right? That point, intersection. Okay. Now, let's just go ahead and calculate what sine theta would be and what cosine theta would be. Okay, so let's start with sine theta. Sine theta of that triangle, right? That's a right angle triangle. We can calculate sine theta. Sine theta is opposite over hypotenuse, right? So opposite over hypotenuse. The thing is that hypotenuse is 1. So this is opposite over 1. I want to note that that's not 0, right? So that's why I kind of like, I'll call this OP still for opposite, just so it doesn't look like a 0, right? Now, anything divided by 1 is just that number. So sine theta is just equal to the opposite length. Sine theta is just equal to that length. Okay. Important. That's an important point. Sine theta is just equal to that length. Now, similarly, oops, not want that in green. And then similarly, we'll do that for cos theta now. So cosine theta is adjacent over hypotenuse, but the hypotenuse is 1. So cosine theta is equal to adjacent over 1. In other words, cosine theta is equal to the adjacent side. Cosine theta is just the adjacent side. So let's combine everything we know. We know that x is equal to the adjacent side. In fact, I'll write the whole symbols for it. X is equal to the adjacent side, right? And that cosine theta is equal to the adjacent side. We know that y is equal to the opposite side, and that sine theta is equal to the opposite side. So if x is equal to the adjacent side, and cosine theta is also equal to the adjacent side, then x must be equal to cos theta. In other words, x equals cosine theta. Okay? And then similarly, if y is equal to the opposite side and sine theta is also equal to the opposite side, then y equals sine theta. Y equals sine theta. And that is how we relate x, y, and sine and cosine. X, y, sine, and cosine of theta. Right? X is equal to cosine theta, y is equal to sine theta. And essentially, now we have a way of finding cosine theta. Let's just say I want to find cosine 30, right? Let's just say I want to find cosine 30. How I would do that, right, is I'd set up something like this. I'd set up a triangle like this, make this angle 30 degrees, find the point of intersection of the ray, the terminal arm, and the circle, and the x value of that point is cosine 30. And the y value of that point is sine 30, right? So I can use this method to figure out what cosine and sine is, right? Cosine and sine is not, they are not just, their normal definitions, adjacent over hypotenuse, opposite over hypotenuse, right? They're also additionally defined by this, that they're the x and y coordinates of the point of intersection of the terminal arm and the unit circle, where the terminal arm makes an angle theta, with the positive x-axis. That's a lot to dig in. So if you want to pause, rewind, look at all those steps again from the beginning, right? Definitely do that. Okay, in fact, I recommend everybody do that once. Stop, rewind, go back to where I started talking about here, started talking about the unit circle. Look at all that again, right? And make sure you understand how we get to this, because this is important. This is how we find sine and cosine, right? For any random angle. Okay. So the method that we have to do this, if I were to just put this in like a point form, right? If I were to just put this in point form, can I find it? Yeah, here we go. If I were to put this in point form, is this method to calculate sine theta and cos theta. Step number 1, draw a unit circle in the xy plane. Step number 2, draw a line connecting the origin to the circle, which makes an angle of theta with the positive x-axis, right? That's that angle right in there, angle theta. Determine the point of intersection of the two, it shouldn't be two lines, oops, that's a mistake. I'll correct that. Of the line and circle. Okay, let me note that here quickly so I don't forget to do that. But yeah, so that would be the next step. And then work now, of course, right when I'm in the middle of this. 117. Okay. And then once we know that the x and y point, then cosine theta is the x value, sine theta is the y value, and then tan theta, remember tan theta is sine over cos. So y over x, right? Sine is y, cos is x, y over x. Okay, so the hardest part is part 3, right? This is the thing that trips trips the whole problem up, right? Determine the point of intersection of the line and the circle, right? That's a hard thing to do, right? And so essentially what we want to do is we want to, for the rest of this lesson, I'm quite certain, show sine cosine for 90. Yeah, essentially what we want to do is we want to do that for specific, well, not the rest of the lesson, sorry. The next part of the lesson is going to be talking about how do we find for angles 30, 60, 90, and 45. Okay, we're going to be looking at these specific angles, and then we're going to be looking at, after that, these angles in other quadrants. Okay, and then we're going to be going through just some examples here. So let's do this method for a 30-degree angle. Okay, let's do this method for a 30-degree angle. We're going to start with first, draw a unit circle. So I'm going to make the xy plane here. The xy plane. Okay, draw a unit circle. Now, I'm going to just draw it as like a few squares, right? So it doesn't particularly matter. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, the next one over. And then there. Oh, one more over too. So there is our unit circle. It doesn't have to be perfect. This is just to kind of guide us along. That's a unit circle, right? Next step is draw a line connecting the origin to the circle, which makes an angle of 30 degrees, right? So now I'm going to just kind of eyeball it, right? So the graph doesn't really matter, right? The math matters, right? So the graph is here to sort of help with the math, right? So that's theta, right? That's, in fact, exactly 30 degrees, right? Let's just say it's exactly. Okay. And now, let's see here, right? Determine the point of intersection of the line and the circle, right? Determine what this point is, right? What the value of that point is there. And then we're going to just use that to help us out a little bit. So essentially, what we want to do is we want to construct this triangle, right? We want to construct this triangle right here, right? Knowing only 30 degrees and that this length is 1. Okay. Now, I can't use trig to help figure out what these other lengths are. That's usually what we would do, right? Use the SOH CAH TOA to figure out what these other lengths are. But right now I'm trying to figure out what sine 30 is, what cosine 30 is, what tan 30 is. I can't use that when trying to figure out what it is, right? I can't use tan 30 to figure out what tan 30 is. So what I'm going to have to do is I'm going to just have to take this triangle out. I'm just going to draw it on the side here, right? And that's always the next best step because we want to kind of get away from the circle. We know that this angle is 30 degrees and this length is 1. Okay, let's try to find the other lengths using some other method that we know. Okay. Now, the next steps that I'm going to show you, you don't have to memorize this, right? You don't have to memorize this. We're just trying to get to the final product you should memorize, the final thing we get. But how do you get from this to the final product? Don't memorize that. Just try to understand it as I'm going, maybe rewatch it to make sure you understand, and we'll go from there. What we're going to do is we're going to start with a seemingly unrelated triangle, okay? A seemingly unrelated triangle. It is an equilateral triangle. All these lengths are the same length. and all the angles are 60 degrees inside. Okay, all the angles are 60 degrees inside. Also, all the lengths are 1. Okay? Okay. Now, what I know is that if I split this angle right down the middle, I know that it'll be split into two 30-degree angles, right? Two 30-degree angles. And additionally, what's this length here? This length was 1, but this length is now a half. So if I just pull out this triangle like that, just that left half, or the right half, but I'll just use the left half, right? We have a right angle triangle, first of all, because I split it right down the middle. The bottom length is a half. This length is 1. We don't know what that length is, but we know that this angle is 60 degrees, and this angle is 30 degrees. Look, we're actually pretty close to this one already, right? 30 and 1. 30 and 1. One angle is 30. The angle, hypotenuse, the hypotenuse of that triangle is 1. We're actually really close. We figured out that other angle is 60, right? And we also figured out that that bottom length should be a half. In fact, we can find this last length just using the Pythagorean theorem. A squared plus b squared equals c squared. A is the one of the two shorter lengths, so I'm going to say 1/2 squared plus b squared. B is what we're looking for here. That's b. Okay, equals c squared, but c is 1, so c squared is 1 squared. And now we just solve for b, which is going to be 1/4 plus b squared equals 1. Solving for b, it's going to be b squared equals 1 minus 1/4. Okay. B squared equals 3/4. Square root both sides. B is equal to the square root of 3/2. Okay, and there we have it. B is the square root of 3/2. Right? And this is called a special triangle. It is a triangle that exists that has 30 degrees and 60 degrees as its main angles, and then 90 here as well. So we call this the 30, 60, 90 triangle, right? And in fact, you can scale this triangle up and down as much as you want, right? You can scale it, you can multiply all the lengths by 2, and the ratio of the sides will all stay the same. That's what we usually care about. So this is the 30, 60, 90 triangle. Okay, I'm going to draw it a little nicer here, right? Bottom length is a half. We have a right angle. We have 60 degrees, 30 degrees, right? 1 square root of 3/2. You would never be able to guess that that length is square root of 3/2, right? In fact, even if you built this triangle without that length and then measured it, you'd still not be able to tell that it's a square root of 3/2. Your ruler probably doesn't have a mark that says square root of 3/2. The only way we found out that that was exactly that was by using the math here, right? Building another triangle, splitting it in half, and then getting what we got. Okay, so this is our first special triangle, and it lets us now calculate what sine 30 is. Sine and cosine 30. Because look, this is our angle theta. This is opposite, this is adjacent, and this is hypotenuse. So now finally, sine 30 is equal to, well, opposite over hypotenuse, 1/2 over hypotenuse is 1, so 1/2. Cosine 30 is equal to, well, adjacent over hypotenuse, so square root of 3/2 over 1 is just the square root of 3/2. And then tan 30 is equal to, well, sine over cos, so 1/2 over root 3/2, which is 1/2 times 2 over root 3, which is 1 over root 3. So that's how we figured out originally, without a calculator, what sine, cos, and tan of 30 is, right? And so calculators use a method like this. Like, of course, they don't do drawing. They have a whole separate set of methods. But you can think of this as like, this is the calculator. This is how the calculator knew. If there was someone punching in the numbers into the calculator, this is how you figure it out without using a calculator. And there's actually a method for almost every single angle, right? For every single angle that you can imagine, like cosine of 26, right? What's cosine of 26? Well, you use a whole bunch of properties to figure out what cosine is 26. It gets a lot more complicated. That's what the whole field of trigonometry really is finding cosine of different angles. Right now, we know how to find it for all the angles, right? We know how to find cosine of all the angles, or sine of all the angles. And we know how to approximate it as much as we want, right? But for 30, 60, 90, and 45, these are the simplest ones. That's why we go through it in this video, right? But yeah, so you can get much more complicated ones. You can go through these long proofs of what the sine, cosine, and tan of an angle is. It takes some time sometimes. Okay, let's now do, well, 60 is actually using the same triangle. 60 would be right here. So let me just get that. Let me copy this triangle down here. If I want to do now sine 60, cosine 60, cosine 60, and tan 60, right? All these things. Then what we're going to do for that, well, essentially, we just say, okay, well, now this is theta. This is now theta, right? This is opposite. This is adjacent. This is hypotenuse. So now sine is opposite over adjacent. Tan is opposite over adjacent, but sine is opposite over hypotenuse. So root 3 over 2 over 1, which is just root 3 over 2. Cosine is adjacent over hypotenuse. 1/2 over 1, which is 1/2. And tan is just sine over cos. So root 3 over 2 over 1/2 is just going to be root 3 over 2 times 2. 2's cancel, and we just get root 3. So there we go. Using this one triangle, we found sine, cosine, tan of 30 and 60. Okay, so there's that for 30 and 60. Now, that's our first special triangle, the 30, 60, 90 triangle. Now we're going to look at our second one. And this is going to help us find what going to help us find what, if I can speak, the sine and cosine of 45 is, right? 45. So to end this method here, right? The last part of our method was just figuring out the x and y value of the point. That's essentially what we did, right? These lengths is the x and y value. That's the x value, that's the y value, right? And that's 1, right? So notice here how that ended up being the x value of the point. If you kind of imagine taking that triangle and flipping it to go into that point, right? Go into that, lay on top of that triangle there. Flip it to the side, you see, well, yeah, root 3 over 2 is that length, right? And then 1/2 is that length, right? So that's how that ended up being just, well, 1/2 and root 3 over 2, right? And so that was the x and y value. And so cos ended up being that, sine ended up being that, and similar for over here with 60. Right? Okay, so now for the 45-degree triangle. Let me just find this. Right. The 45-degree triangle is called the 45, 45, 90 triangle. 45, 45, 90 triangle. And let's start out the same way, so we start with our x and y grid. We then draw a unit circle. Of course, unit circle doesn't have to be perfect, right? Draw a 45-degree angle. Okay, that's 45 degrees, 45-degree angle there. Okay, and we're going to take this triangle out, and we're going to see how we can, we know that length is 1 there. So we're going to see how can we construct the 45, 45, 90 triangle without using trigonometry, right? Because the point is to figure out what the trigonometric ratios are, what cosine 45 is, right? So 45 degrees there and 1 there. So we got to find the other lengths. Well, one thing we know for certain, right, is that this angle in here is 45 degrees as well. Because the inside angles of a triangle have to add up to 180. So 90 plus 45 plus 45, right, is going to give us that. So that's why it's called the 45, 45, 90 triangle. Okay, let's continue deriving this triangle. How we're going to do it is we're going to start with actually a square. And remember, the process of getting to the special triangle, you don't have to memorize. But the actual special triangle, I mean, you don't have to memorize it. You can just have it in your notes, right? But it is very useful to know. we're going to start with this square. The square has a side length of 1 on each side. And we're going to split that square down the middle, diagonally. Each of these corners used to be right angles, but now this is a 2 45-degree angles, another right angle, and 2 45-degree angles, right? 2 45-degree angles. So we've essentially actually got the triangle here, right? We've essentially got this triangle, right? Almost to the point that we care about, right? Oops, that's not what I meant to do, right? So this is what we care about there, that section. Let me just highlight it, right? We essentially have the triangle that I was talking about up here, right? From the square. So let me pull that triangle out. We have I'm going to turn to the side a little bit too, right? Flip it to the side. So we have a right angle there. This is a 45-degree angle. This is a 45-degree angle. And this is 2 lengths of 1. Okay? So we have to solve for the hypotenuse here. And you're going to notice the hypotenuse is not also going to be 1. But we're going to deal with that in a second, right? We're looking for when the hypotenuse is 1. But for now, let's just figure out what the hypotenuse is here, and then we can work from there. So the hypotenuse, right, we can just find with Pythagorean Theorem, a squared plus b squared equals c squared. So 1 squared plus 1 squared equals c squared. So 1 plus 1 equals c squared. So 2 equals c squared. So the square root of 2 equals c. Pause if that was too fast, right? But we figured out that the square root of 2 is that missing side length. This is the square root of 2, that length there. But that's not 1, right? We want it to be 1. So remember, we're allowed to scale the triangles as much as we want in trig, right? Stretching a triangle out or compressing it down, multiplying all the lengths by 5 or dividing all the lengths by 5, it doesn't matter, right? The ratios, the trig ratios are the same. So we're going to do that. We're just going to go in here. We're just going to divide. I'm going to write that here. Divide all the lengths by root 2. Divide all the lengths by root 2. That's how you write it in text. You write square root 2. So root 2 divided by root 2 is 1. Well, you know what? How about I just copy this triangle here? Okay. So root 2 divided by root 2 is 1. 1 divided by root 2 is 1 divided by root 2. And 1 divided by root 2 is 1 divided by root 2. And there we have it. We know the x and y values of that point, which tells us that, that length there is cosine theta, and that length there is sine theta, right? So we just learned that sine 45 is equal to 1 over root 2, and cosine 45 is equal to 1 over root 2 as well. If you type it into your calculator, you may get root 2 over 2, but that's actually the same number. Okay. And you'll learn about why that is. Not very important why that is. They're just the same number. They're just written differently. So sine 45, cos 45 are both 1 over root 2. Okay, and then tan 45, well, tan 45 is sine over cos, but sine is equal to cos, right? So for 45, for the angle 45, right? So tan 45, well, that's just going to be 1, because 1 over root 2 divided by 1 over root 2 is just 1. So tan 45 is 1. Okay, so here's our other special triangle, the 45, 45, 90 triangle. In fact, do I have it in the notes here? It's probably best if I just, instead of just trying to draw this myself, let's just get it from the notes here, right? So there it is. If I just zoom in a little bit to make the quality a little bit better. Right. So there's that one, and then here is. Okay. So, whoop. No, something by accident. So here is our, that's not the 45, 45. This is the 45, 45, 90 triangle. And it's usually written with a root 2 there, right? It's usually written with a root 2. Instead of having a 1 there, it's just written with root 2. But remember, you can scale all these triangles as much as you'd like. Oh, sorry, that's supposed to be a 1 down there, right? So again, this isn't the same triangle that we set up here. But look, if you just multiply everything by 2, all the side lengths by 2 here, you get this triangle, right? So 2, root 3, and 1 is the same special triangle. These are the two special triangles, the 30, 60, 90 triangle and the 45, 45, 90 triangle. These are the triangles used to figure out what the sine and cosine of 45 and 30 are, because these are triangles that exist, right? These specific with these exact lengths. Okay, so that is essentially that part of the lesson done. I'm quite certain, right? Show. Oh yeah, and then for 90 as well. Okay, so then for sine and cosine and tan of 90, we can go through the method, but it's actually going to be a little bit different, right? So if I go through the method again, right, we start by drawing a unit circle. So we're going to do 90 now. Sine, cosine, and tangent of 90. And then I'm going to draw the terminal arm with an angle of a 90 here, right? What's this point? Okay, first of all, its x value is 0, right? It's on the y-axis. And its y value, well, it's just the radius, 1. So that's the point 0, 1, right? And this tells us that cosine, remember, x is the cosine, y is the sine value. So sine of 90 is equal to 1. Cosine of 90 is equal to 0. And now what's tan of 90? Tan of 90 is sine over cos, 1 over 0, which is undefined. Not a number, right? 1 over 0 is not a number. So tan of 90 is actually not a number that exists. Tan 90. So you're going to see that actually there's numbers that you cannot put into these functions, right? There are some numbers that you cannot put into these. Remember, you know, the domain is the set of all inputs. So the domain of sine and cos is all real numbers, but the domain of tan has a couple holes in it, right? There's a couple holes in the domain of tan, a couple restrictions, right? Essentially, whenever cosine is 0, right? Whenever cosine is 0, because remember, tan theta is equal to sine theta over cos theta. So whenever cosine is 0, tangent is equal to a fraction with a denominator 0. Well, that doesn't exist. So there's a couple holes there. That's just an interesting thing to add on. Okay, so I have another whole section to this lesson, right? We're pretty far into it. It's an hour and 41 minutes for me into this lesson. But we have another whole section, which is to deal with angles that are greater. So angles that are greater than 90 degrees. Okay, and not any angle, right? Just like we didn't do any angle between 0 and 90, right? I didn't talk about sine of 26, right? Because that's a really long process, right? At that point, you're just gonna have to trust that your calculator knows what sine 26 is, right? But there is some stuff we can do for angles greater than 90. Okay, you can still find the sine and cosine for a couple angles greater than 90 using the method using only these two triangles. Okay, and the method I described above, but using these two triangles. Okay, so let's talk about that. So let's pretend like we wanted to find the angle, like the sine and cosine of an angle like, let me just decide here what we're going to do, like 150. Okay, 150 degrees. Sine 150, cosine 150, and tan 150. That's what we're trying to find. I'm going to show you why this would be really hard with the method that I described above, right? This method here. This one, right? It would be really hard to do this. And the reason is because let's give it a try, right? So if I put the x and y axis on here, and then I draw the circle in, right? Like that, right? The angle 150 is like here, right? That, remember, we always measure from the positive x-axis. That's the angle 150, right? Bigger than 90, less than 180 though, right? This is 180, right? And so now this triangle, to try to draw this and try to figure out the lengths inside that, it's not even a right triangle anymore. We can't even use the Pythagorean theorem anymore, right? So that would be really hard. That would be really hard to do, right? So what we end up doing, right? What we would end up doing is we actually use what's called a reference angle to solve this. And the essential idea is that we draw a line. Well, essentially we take this angle, we take this angle right there. I'm going to call that phi. Okay, like another angle, right? Phi. Not the same thing as theta. But yeah, I'm going to take that angle, and that angle right there is called the reference angle. So phi is the reference angle. In words, it's the angle between the terminal arm and either the positive or negative x-axis, whichever one's closer, right? That's the positive x-axis. That's the negative x-axis. So what we want is to be able to see how does that angle theta, that angle phi, relate to sine, cosine, and tan of theta, right? Theta is 150 in this particular case, right? Write that in blue just so you can see 150, right? What's phi? First of all, what's phi? Well, we know that 150 plus phi would be 180, right? 150 plus phi would get us fully to 180. Hopefully you see that in the graph, right? That's 150. A little extra is phi, and that gets us to 180. So that tells us that phi equals 30 degrees, right? So we know phi is 30 degrees. Now, but how does cosine, or like sine of phi, cosine of phi, and tan of phi, how does that relate to what we're really trying to find, which is sine of theta, cosine of theta, and tan of theta, right? Because we can find sine of phi now, sine of 30. We know how to find sine 30, right? Sine 30 is something we just went up here to figure out how to do. Sine 30, where is it? Sine 30 is 1/2, right? But that's not sine theta. Theta here is 150. So how does it relate? Well, what you do is it's actually just plus or minus that, right? It's actually just plus or minus, okay? And how you decide if it should be plus or minus, right? Whichever one you have, right? I guess maybe the plus or minus should actually go on here, right? So either we want plus or minus the sine of phi, and that's going to give us sine theta. So how you decide if it should be positive or negative is using a rule called the cast rule. So essentially here, right, if I want to find sine theta, right, then so in this particular example, if I want to find sine, I'm going to rewrite it here a little bit, sine 150, well, that's going to either be plus or minus sine 30, right? Cosine 150 is going to be the same thing. It's either going to be plus or minus cosine 30. And finally, tan of 150, well, that's either going to be plus or minus tan of 30. But again, how do we decide if it should be plus or minus that? Right? So how we do it is using the cast rule. Okay, so it's called the cast rule. Cast. And we look at the quadrant that the terminal arm's in, and we decide, is sine, cos, and tan, are they positive or negative in that section, right? So look here. If I just use the method like we had before, right? I draw a unit circle on a pair of axes, right? A pair of axes like that. And my terminal arm ends up here. Remember that our x coordinate is the cosine, and our y coordinate is the sine of, right, that angle. The thing to notice here is that our x coordinate is negative, right? Our x coordinate is negative, but our y is positive. So I'll write that actually just in symbols, right? So I'll say y is positive, right? X is negative. That tells us that here sine, or I guess cosine, sine is positive and cosine is negative. And what about tan? Well, remember, tan is sine over cos, so a positive number over a negative number. Well, a positive number over a negative number is a negative number, so tan is negative, right? So in the second quadrant, sine is positive, cosine's negative, tan is negative. What about in this quadrant, for like a point here? Well, y is negative and x is negative. So sine is going to be negative. Cosine is going to be negative. Tan is going to be positive. Negative divided by a negative is a positive. Okay. What about here? Here we have our x values positive, our y values negative. So that tells us that cosine is positive, sine is negative, and tan is sine over cos. Negative divided by a positive. Negative divided by a positive is a negative. And finally here, well here, y is positive and x is positive. So that means that sine is positive, cosine is positive, and tan is positive. So we just actually have to do that, right? We know we're in the second quadrant, so we know that cosine and tan should be negative, but sine should be positive. So you choose the positive one for sine, the negative one for cos, and the negative one for tan. And the way to memorize this, instead of having to derive this the whole time, every time you go through this whole process, is just memorize what's positive in each quadrant. Sine is positive here. Tan is positive here. Cosine is positive here, and they are all positive here. In other words, cast. C-A-S-T. Cosine's positive, all's positive, sine's positive, tan's positive. Everything else is negative. The other two are negative, whatever you don't mention. Right? Except for all is positive. Right? So here, our terminal arm was in the second quadrant. In the second quadrant, only sine is positive. So sine of 150 is positive sine 30, negative cosine 30, and negative tan 30. The reason that we're allowed to just do plus or minus here is because, look, we really still have a 30, 60, 90 triangle here. It's just that some of the lengths are negative, right? So that's why that sine 150 is plus or minus sine 30, plus or, or for cosine, it's cosine, for tan, it's tan 30. Right? It's because we really have a 30, 60, 90 triangle in there. It's just that that length is negative now, right? Or if we were in the bottom quadrant, right, then that length, and that length would both be negative. So here is just a little diagram to help with remembering the cast rule, right? So if I have, here is just, essentially this is good. Screenshot quickly, and then we have essentially a new method to figure out angles that are greater than 90. So we're finishing up. I know it's a very long lesson, but we're finishing up. Cast rule looks like that. Make sure you don't, very, very common mistake is to say cast, because you always want to start in the first quadrant, right? But that's not the rule. It starts here, right? Cast, the C starts here. And some people like to prefer to remember just ASTC more. But you still call it the cast rule because at least it has a name, right? So a normal word. So cast like that, right? Start here. Then we want to just look at what does it mean, right? So in quadrant 4, cosine is positive while the rest are negative. In quadrant 1, they're all positive. Quadrant 2, sine is positive while the rest are negative, and quadrant 3, tan is positive while the rest are negative. Right? Okay, and so this brings us to our new method to calculate sine and cosine for angles greater than 90. Right? So essentially, you have the same process, right? Draw a unit circle in the xy plane. Draw a line connecting the origin to the circle so that it makes an angle of theta with the positive x-axis. The difference is now calculate the reference angle theta of the terminal arm. Calculate sine, call that angle phi. Calculate sine phi and cosine phi using the earlier method, right? You might already know it, maybe use a calculator, whatever, right? And so that's how you would figure out, right, what sine and cosine are for angles greater than 90. And essentially, that brings us to the end of the lesson. I'm just going to go through a bunch of examples now. I have essentially 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 examples of doing this, right? So probably won't take too long. Let's just see how quickly we can get through this while still explaining things properly, right? So first of all, find cosine 30, right? So this is stuff we already did, right? Cosine 30. In fact, I guess I'll skip that because we already found, I showed how to find cosine 30. I showed how to, showed how to find cosine 30. We did that up here with the 30, 60, 90 triangle, right? You use the 30, 60, 90 triangle to find adjacent over hypotenuse, right? So root 3 over 2. Sine of 90, I showed how to find that, right? You do draw the terminal arm straight up because that's a 90-degree angle. And then sine of 90 is the y value, which is 1. Cosine 45, I also showed adjacent over hypotenuse. Tan of 90, I showed that it was this. Okay, tan of 60, I don't know if I showed that. Oh, no, I did show that, right? Tan of 60 we also showed, so right here. And it's good if you go through this. This is going to be in the practice word too, probably. Find tan of 60. Show all the steps to find tan of 60, right? Without a calculator, right? And so there's quite a few steps in there, right? So make sure you're able to replicate this. Definitely watch some parts of this video again if you have trouble. This is a long one, I know. Tan 45 we already talked about. Sine 60 we already talked about, so I'm going to skip those. So you know what? I actually only have a couple left, right? So find cosine 150. I showed that here. Cosine 150. I guess you know what? Let's actually finish this problem. I didn't finish this problem, did I? So sine 150 is sine 30. Sine 30 was, let's see what sine 30 was. Sine 30 was just using this triangle. Sine is opposite over hypotenuse, so 1/2. Cosine 30 is adjacent over hypotenuse, root 3 over 2, but it's going to be negative root 3 over 2. And tan is opposite over adjacent, so 1 over root 3, but it's going to be negative 1 over root 3. Right? So we finally show that cosine 150 is a half. Sorry, sine 150 is a half. Cosine 150 is negative root 3 over 2. And tan 150 is negative 1 over root 3. Okay. So there's that. Now let's do, essentially I'll do two more examples. So I'm going to do, we're going to look for sine, cosine, and tan of 240, right? Of 240, and sine, cosine, and tan of 300. Okay, those are the two things we're going to look for. Okay. So let's take a look here now for 240. So first step, draw the unit circle on the xy plane. So there's our unit circle. There's our xy plane. Okay. Draw a line connecting the origin, right, to the circle that makes an angle theta with the positive x-axis. So 240, this is 180. This is 270. So 240 is going to be like there. Well, not really there, but there. Right? Oh, actually, I guess it passed 45. Doesn't particularly matter, as long as you get the numbers right. The drawing doesn't really matter. So that angle is 240. What we're interested in is calculate the reference angle. The reference angle is the angle between the terminal arm and either side of the x-axis, the shortest side. So that angle is our reference angle. What is that angle, right? Well, one thing we know is that 180, so 180, not that color, so 180, okay, plus phi, plus our reference angle, is equal to 240. So hopefully you see how that is. 180 plus phi is equal to 240. So this tells us that phi is equal to 60 degrees, right? It's going to be 60 degrees there. So now I know that sine of 240 is equal to, well, plus or minus sine 60. Cosine of 240 is equal to plus or minus cosine 60. And tan 240 is equal to plus or minus tan 60, right? Now, should it be plus or minus? Well, we determine that using the cast rule. So I'm going to put the labels here, cast. In this quadrant, only tan is positive. Only tan is positive. So this is going to be minus, minus. Only tan is positive. So finally, we just figure out, okay, well, what's sine 60 now? That's the whole other thing. Well, we look back. What did we figure out for sine 60 using this triangle? Sine is opposite over hypotenuse, so root 3 over 2. So this is going to be negative root 3 over 2. Cosine 60 is adjacent over hypotenuse, so adjacent is 1, hypotenuse is 2, so 1 over 2. But it's going to be minus 1 over 2. And tan 60 is opposite over adjacent, so root 3 over 1, which is just root 3, so it is just root 3. So sine 240 is negative root 3 over 2. Cosine 240 is negative 1 over 2. And tan 240 is root 3. Okay, let's do now for this one. Sine, cos, and tan of 300. Again, start by just drawing a unit circle in the xy plane. Okay, xy plane like that. Draw your angle of 300. 300 would be something like this. Okay, something like that. Right, that's 300 degrees. And now we need to find the reference angle. The reference angle is going to be that angle. Right? That angle right there. That's our phi. And the one thing we know is that 300 plus phi gets you to 360. Right? 300 plus phi is 360. Hopefully you see that. 300. And then you go phi more degrees, you get 360. Okay, and that tells us that phi is equal to 60 again. So again, sine 300 is equal to plus or minus sine 60. Cosine 300 is equal to plus or minus cosine 60. And tan 300 is equal to plus or minus tan 60. And now you got to figure out what sine, cosine, and tan of 60 are. Well, we already figured that out, right? But actually, the first thing is to even figure out if it should be positive or negative. We do that using the cast rule. So in the fourth quadrant, only cosine is positive. Everything else is negative. So now we know that, well, negative sine, so sine 60 was root 3 over 2, so it's going to be negative root 3 over 2. Cosine 60 was 1/2. It's going to be positive 1/2. And tan 60 was root 3. That's going to be negative root 3. And there we go. So that's how we find sine, cosine, and tan for angles greater than 90. Okay, all the way around the circle. And then you can keep looping, right? I could go to 360, right? Notably, the very important thing to note here, which is going to come up a lot in the next chapter, is that 360 is the same as 0, right? The angle 30 degrees is the same as the angle 390, because you go 360 and then 30 more. So that's actually the same angle, right? And so we can use that method to find angles more times, but you wouldn't really want to do that, right? This is, we're going to use that in the next chapter to help us out a little bit, but yeah, that's the idea. And so if you collect, right, sine, I'm just going to copy and paste this because I typed this before, so I don't want to type it all again. If you collect sine, cosine, and tan for the angles 0, 30, 45, 60, 90, 120, 35, 150, 180, 210, 225, 240, 270, 300, 315, 330, and 360, okay? These are all equally spaced bits, okay? They essentially, equally spaced, almost equally spaced. And so essentially we're going up by 30, 45, 60, 90, and then the equivalent in the next quadrant. So 30 more, 45 above 90, 60 above 90, and then 90 above 90. And then again, 30 above 180, 45 above 180, 60 above 180, and then 90 above 180. And then again, right? If you collect all that, you get the unit circle, okay? And which is different than a unit circle you draw on the xy plane. The trig unit circle, okay, if I just look up an image of that, it has a lot of numbers all over it, right? And essentially that's what they did, right? Kind of ignore these pi's. Anything you see pi, ignore that, because that's in radians. Okay, but what I want you to look at are these points, right? The angle 0 has has the point 1, 0 there. So cosine of 0 is 1. Sine of 0 is 0. Right? Cosine of 30 degrees is root 3 over 2. Sine of 30 degrees is 1/2. And you can complete this whole table yourself just by using all the things we learned in this section here. And then from there, you will eventually be able to find all the angles, right? And they're very useful. They come up a lot, these specific angles. Okay, so what if, this is the end of the lesson. That's everything. That's all the topics I want to do. That's all the examples. I know it's a really long one. This is, I'm recording for 2 hours now. But I want to just add one thing here, which is that, how do we find cosine of, I don't know, like 1 degree, right? There's a whole process to prove this, to prove what cosine of 1 is, right? Just like how we found cosine of 45, we had to make a triangle, cut a shape in half, There's this whole long thing for cosine of 1, much more complicated than what we do here. The last thing I have to mention is that for a lot of angles like cosine of 1 or something like that, right, we use a different entire method to approximate it, not get the exact answer, but to approximate it to any kind of degree of accuracy we want. We want 200 decimal places of cosine of 1, then we can get that, right? And so we use something called the Taylor series for that, and that's something you'll learn very later on. But just so you know that we have methods to not only get the exact answer, but also methods to approximate it as close as we want to, and that's usually done a lot in engineering. Okay, well that is now everything for the lesson. Let's do a review quickly of what's happening, and then that will be it. So first of all, we did a big review of SOH CAH TOA, right? Did a big review of SOH CAH TOA. This is probably the longest lesson of the unit, so that's why this took a while. Review of SOH CAH TOA. Okay. We did a lot of stuff there, right? We then made the method to find sine, cosine, and tan of 90, of theta, where theta, up to 90, I'll just say up to 90, right? Theta is up to 90 degrees. And that was with the unit circle and the terminal arm and angles there, right? We saw how cos is the x value, sine is the y value. We then talked about our 2 special triangles, okay? And we use that to find sine, cosine, tan for 30, 60, 90. Yep, exactly that. Then we started talking about angles greater than 90 and how we use reference angles for that. Right? We use reference angles along with the cast rule to determine if it should be positive or negative. And then we went through a good amount of examples littered throughout the whole thing. Okay, well that concludes the lesson for today. Thank you so much for watching. I know it's a long one, so hopefully you you got a chance to pause and maybe rewatch some parts, rewind if you were getting confused and all that. That's the good thing about being on video. So we can book a session with me or another instructor. By going to the information page for this website, or you can email me at secondteacherprogram@gmail.com. Okay, that's everything for this lesson. Thank you so much for watching. Definitely check out the practice problems for this section because there's going to be a lot of good ones, and hopefully won't take, definitely needs practice, right? So yeah, thank you so much for watching. I hope you enjoyed, and I hope you have a great day. Thank you for watching the video. Remember, if you want me to teach you the entire course, visit my website, tutor.ca, and enroll in the Second Teacher program, which includes video lessons, private tutoring, notes, and practice problems for every section in grade 11 functions. Have a nice day.